Hello, this is Stuart Mason here from Math E156 with Script 7b. We're going to be constructing some classical confidence intervals off the student's t-distribution. So first, a quick review. We're going to be discussing a situation where we know the population variance but not the mean. This can arise in the real world, however it's really more just an illustration because usually we don't know anything. But let's pretend we know that the variance is 16 and the mean is 25, but that's unknown to us, and we're going to compute 95% confidence intervals on samples. So we're going to initialize a counter variable. This is going to count how many times our interval succeeds in capturing the true mean, and we're going to set up a blank plot that'll be helpful in a minute, and let's walk through what this for loop is going to do. So 1,000 times we are going to draw 30 samples from our population. And then we're going to compute the lower bound of the confidence interval, which will be the mean plus the 2.5% quantile of the normal, which is negative 1.96, times the scaling factor to convert this quantile into the space of our actual sample. And then the upper bound is very similar, except now using the 97.5 quantile. This scaling factor is the square root of the number of the samples and the standard deviation in the numerator. And we're going to say if the lower is less than the true mean and the upper is greater than the true mean, that means our interval has enveloped the mean, and we're going to increment our counter. And for the first 100 such examples of this, we're going to draw a segment at height I that spans from L to U. Let's do it. Okay. We'll add an AB line at 25 to show where the true mean is in this space, and you see that basically some of our intervals surround this mean, and some of them, like for example right here, completely missed the mean. This code, counter divided by 10,000, will tell us exactly what percentage of the time we found the true mean, and 95.8, so we got a little bit lucky. Looks like 8 more than we would have expected of our 1,000 samples surrounded the mean, but this, I hope, serves to illustrate the key frequentist idea here, which is that the mean is fixed. With probability 1, the mean is 25. With probability 0, it is anything else. We randomly, based on samples, construct these confidence intervals, which 95% of the time will capture the true mean. And just to show where these 1.96 value comes from, we're going to explicitly ask for the quantile of a normal at 0.025 and 0.975. Sure enough, 1.96, negative 1.96. Okay, so that's a nice review of how this works, but what happens when we don't know the standard deviation? Well, when we don't know the standard deviation, we can estimate it using the sample standard deviation. However, this estimation adds an extra level of uncertainty, and so our confidence intervals become necessarily a touch wider. How much wider? Well, as much wider as is determined by the quantiles of the relevant student t-distribution. So this code is again going to be very similar. We're going to initialize our counter at 0 and draw a blank plot. We're still drawing 30 samples from a random normal at mean 25, variance 16. But this time, instead of having 4 in our numerator of the confidence interval scaling factor, we're going to have our sample standard deviation, and instead of using quantiles from a normal, we're using quantiles from a student t with 29 degrees of freedom. This 29 is 1 minus our sample size. So let's run it and see what happens. So looks like we captured the mean again just about 95% of the time, as well we should because the assumptions powering these confidence intervals are met. However, in general, these confidence intervals are going to be wider than their counterparts in the case where we knew the variance. If we were to use 1.96 and negative 1.96 here, we probably would have gotten slightly less of a success rate than 0.947. And just to be explicit, here are the quantiles that we are using in the code. So we're going to ask for the 2.5% quantile and the 97.5% quantile with 29 degrees of freedom. And you see it's negative 2.04 and 2.04. So slightly larger than the normal case, and so that's going to serve to make our confidence intervals wider. And just to be a little more illustrative, let's crank down the degrees of freedom and see what that does to our quantile value. Let's say we only had 10 data points and therefore 9 degrees of freedom. You see our quantile values get even wider, which will serve to make our confidence intervals even longer. This intuitively shows us why more data makes for a more tight estimation. And Paul shows us that with our t.test function, we can automate this. So x, you'll recall, is just a sample from a normal distribution. We're telling R that we want a confidence level of 95%, and we're asking it specifically for the confidence level attribute. So let's run this code, and it tells you at a confidence level of 95%, with one sample, here's what you can say about the mean, and sure enough, we notice that this captures the mean that we know in this case to be 25. As always, when you're running a test object, you can ask R for a summary, and it will tell you everything that it's computed. So you could replace this conf after the dollar sign with any of these variables, and it would return the relevant information. So if we get a new sample and run the t-test again, we get a slightly different interval, 23.79 and 26.29, instead of 23.06 and 26. But this time, once again, we've captured the true mu. So it's all well and good to run this sort of thing over and over again and show how different samples result in different confidence intervals, some of which capture the mean and some of which don't. With real data, we only have the one sample. So let's read.csv the North Carolina birth weights and only get girls. And we'll try to get a 95% confidence interval for the birth weight of girls in North Carolina. And there it is. So as we saw in 7a, if the distribution is not normal but is symmetric, then the t-distribution still works pretty well. And in fact, we're going to do that here. So this is similar code to before, but now instead of drawing from a normal, we're drawing randomly from a uniform. Paul has gotten a little cute here and rigged the endpoints such that the mean will be 25 and the variance will be 16. Everything else will be the same. So let's run the code and see. Again, some of the confidence intervals capture the mean, some don't, and about 95% of the time it worked. Here's the quantiles we're working with. We've already seen those. Grab just one sample and run the t-test. Cool. Now let's do this again with a skewed distribution. So we're going to use gamma, and with 30 samples, we're not really symmetric enough for the CLT to work, and we'll see if the t-distribution still leads us astray or not. So it looks like in this particular case, we were successful in capturing the true mean, but it won't happen 95% of the time. Let's see how often it does happen. So these are the empirical quantiles. You see 2.5% of the time our sample mean was 23.5 or lower, and 2.5% of the time it was 26.5 or higher, and the mean of all of our means was 25. And it looks like 2.5% of the time the upper quantile was below the true mean, but 3.2% of the time the upper student confidence interval was below the true mean. So you can see it has failed, right? It's too frequently failing to straddle above the true mean. And we can do the same thing for the lower confidence interval. So again, 2.5% of the time is just what we expect for the true distribution, but for the student's confidence interval, it was actually slightly better. And that's probably a function of the fact that the reason this goes wrong is because the gamma distribution is skewed. So on one side, it's kind of nice and normal-ish, and so we get this, basically the lower interval works out. But on the other side, it has this long skewed tail, and that draws the upper value too high. As Paul points out, by sampling 1,000 times and getting these sort of empirical quantiles, we did much better, but that's cheating, right? We can't do that in real life. We're stuck with the data we have, and whatever quirks or messiness it has that makes it not normal. So I hope this is a helpful guide to seeing confidence intervals in action and why they are random. I'd like to point out that this is a very good way to visualize this sort of thing, but many of you, it looked like, explored ggplot in your projects, and I have some thoughts on how you could really spruce these up with ggplot, right? It would be conceivable that you could sort them from lowest lower bound to highest upper bound, and color them, for example, based on whether or not they capture the true mean. Might be kind of an interesting way to really have the difference of these things jump off the page. So if you're interested in putting that together and posting it on the course website, that would be pretty cool. Anyways, see you guys on Wednesday. Hope this was helpful. As always, send any questions to smason@post.harvard.edu. Have a great weekend.